Okay. Hello, everybody. In this lecture, we are going to work with two programs using the global optimization VI in LabVIEW. In general, and in machine learning, we are mostly interested in the global minimum value of the objective function. Local minimum values may be required, but the most interesting for us is the greatest value, the extreme value, which represents the minimum value of the objective function. So this function is very important and has a very common use. But if you look at its at its configuration, as you see, it is here. So if I go to the help and look at the terminals there, we shall find a specific terminal here, this one of the upper side to the left, called objective and constraint function. This really is a specifier, a reference to the objective function. This means that this function exists in the main program and it can dynamically call the objective function and the constraints only when this main program is run. If the program is put to off position, so the objective function and constraints are taken away from the program. This method is used to make economy in the memory of the computer. And it is very often used also. So today we shall work with this terminal. I shall show you how we can realize dynamically calling of the objective function and how we can create it. For such function, usually LabVIEW gives you a template where you can build the objective function alone and save it alone in the computer, and then it will be called by realizing a specific setup. I shall show you that just now. So leaving this page and going back to our program here, you see this is our global optimization function. And this terminal is the reference, gives the reference to the virtual instrument, which includes the objective function. So in order to create the objective function, you should at first go to the help from here, and from there, here I'm going to the help, and from there I open the template which is supplied for use. Here it is front panel and it has a block diagram also window. Normally we build the objective function on the block diagram if we have the objective function already existing somewhere, we can copy and paste it here. In this example, I am going to use the objective function which we have used at the beginning, which is equal to, it is really a quadratic function. It is x squared minus 6x plus 5. To realize it, here we include an index to the array which is supplied here as a terminal, constant 0, and here now we take the output. This represents the value. Let us give it an indicator and call it x. This is the value of x, and it is shown as you see here. Now we want to find to build on this value x, we need to use x squared. We go to numeric. This is the squared of the x here, x squared minus 6x. So we have to multiply by 6. This is create constant 6. We have to multiply x by 6. This is x by x gives 6x. We have to subtract this product from x squared. So we go back to numerics and subtract it from this terminal. And at the end, we have to add number 5. Add the output to a 5, constant equal to 5. This is the output of our function. It has to be converted to an array. We build an array of one value, and now it is ready. So now, after building the objective function here, we save this VI in the memory, and this VI will be dynamically called. I have saved it in the memory under a name. I can show it to you, but instead of saving another time. So let me finish with it and consider that this is already saved. And if we go to our computer, don't save. Now, if we go to our computer here, to the PC, here the optimization with LabVIEW. So here I have saved it. It's called Global Optimization Objective Function 3VI. This is the, if I open it, I shall have, of course, the same thing as I showed you. If I now go to the block diagram, here is the same construction of the objective function, and here it is named. Okay, now we have the objective function. It exists somewhere, and we want to realize the, let me say, the interface between this VI, which is the called VI, and the main program here. For this purpose, at first, we need to create the block diagram somewhere here around the function. We have to create, by using the application control, as you see, a static VI reference. We put it here. Now this static, we can write what its name, static VI reference. Now this static VI reference, as you see, is used as a copy of the objective function. To make that, we need to drag here, I open it again, and as you see, this is the icon of this function. I drag it and put it here. Now I can work with this global optimization objective function which I have created. Okay, now I need also to go to the application control and to fix or to put on the block diagram open VI reference. This open VI reference must be fed by this objective function. Sorry, I cannot do that now. I should now take the address or the path from this function and connect it with the path to the open VI reference. So here I right click, go to create, and create a property VI path and put it here. Now I connect the called VI with this, and the path now is connected with the input here, which represents the path. Now the output of this must be connected with the VI, which is going to call the sub VI here. But for doing that, we need at first to go to this terminal here, type specifier VI refnum. I right click on it and create a constant. And now I go back to this function and drag it here to have the same number and the same setup of connecting terminals. As you see here, this circle as a stop circle appeared, indicating that everything is okay and the terminals are coincident with each other. No problem with it. After doing that, now I can connect the output, this output from here, instead of this one here. Now the program is ready to call. When it is run, it is ready to call the objective function which is existing in our file there. If you look at this setup here, I have done it alone without you. I have added only here a terminal so that to be sure, an indicator to be sure that it is the same function when it is displayed. And now if I go back to the front panel and run the program, I shall get an answer. Here, as you see, the minimum value, the coordinate of minimum value is 3, and the value of the function at minimum is equal -4. And here is the address or the path, again, to the objective function. If you go back to the previous lectures, which are now in my channel, and go back to this function and remember it, you will find that this function was solved differently by using SciPy and by using LabVIEW only and by using other VIs in LabVIEW. And it gives exactly the same answer. What is also interesting, here there is a terminal here, which is the bounds. We should supply the bounds of the function, the objective function which we are going to use. Really, this function has no bounds. So I gave the minimum values as minus 100, minus 100, and the maximum as 100, 100 to give a very big span between them, and the function looks like without any bounds in this case, as you see here. Also, if we go back to the front panel, really we can see the point which represents the value of 3. Here minus 10 to 4, maybe if I put it here minus 10 to, let me say, 7, for example, and here minus 4 to 5, maybe, a good range. So this is the point where we have number 3, x equal to 3 here, which is the coordinate which represents the value of the position where the minimum occurs. And the output exactly the same. It is repeated, and we get the answer after 49 iterations. Okay, with this function, now I think it is clear for you. At least now, for those who did not understand or did not hear before about the dynamic calling of VIs or sub-VIs, now you have a reference and you can work with it. Okay, we leave this example and move to another example. Here is another example also where I used the same function in order to find the minimum of an objective function which has two variables. The previous function has only one variable x. Here, as you see, this is the setup which realizes dynamic calling by this global optimization function. This input represents the bounds of the function. And here we shall have the minimum value here of the function, and we will have the coordinates of the minimum value. Because we have two variables, so we will have x and y coordinates here. If you go to the block diagram, here you have two values, 0.997, 1.000, and the value if minimum of the function is equal 0. Really, this function is also now well known. It is very famous. It is Rosenbrock function, where the value of the function is equal to 0 at the valley, and the coordinates there is 1 and 1. If you want to see the objective function and how it looks like, we double click here now, and we go to the block diagram, and we shall see really that here is our Rosenbrock function, which is equal to x minus 1 squared plus y, this is y now, this is y minus x squared, all are squared, and this is the output. So indeed, this is our Rosenbrock function, and it's okay if we go back and run the program, we shall get, of course, the same answer. But here the limits are different, so I have to change these limits to match with those of Rosenbrock. Rosenbrock, you remember, minus 5.12 to plus 5.12. I can write here minus, for example, minus 5. This will be minus 5. It is within the range. And this will be 5. And this will be 5. These values are within the range of the bounds of the Rosenbrock. Now, if we run the program again, we shall get the same answer, 1, 1, and 0. If we want to work with another program, I have made a test with another program, which is the holder table program, if you remember. If you go back and see what we have there, here it is. The input here is x, here is y, and at the output now we get here the expression, the total expression of the, it is holder table, not holding, holder table, and here is the output. So instead of having the output from Rosenbrock, we connect with the output of holder table. And now if you go back to the block diagram, of course this is not necessary for us. Here we have to change the limits. I have written them aside to remember. So these are the limits of holder table from minus 10, x and y to plus 10 and 10, x and y. So minus 10, minus 10. Here we have 10, and here we have 10. And now, if you look at the setup here of the program, I did not take this cluster and worked it out to make a plotting and or animation. It's simply I want to have the value of the minimum of the function and the coordinates of the value of where the minimum value occurs. So if I go back now and run the program here, I shall get another values, which is minus 19.2. You remember this very well. This is the minimum of the holder table, and this is the coordinates of one of the expected 4 coordinates of the legs of the holder table, 9.66 and 8.05. So really, everything is working fantastic, and there is nothing to explain anymore. Now, one interesting thing also I want to tell you today is how I will show you how to find the expression or the value of any value to the power of any value, the exponent. Now, it takes 2 seconds to open. Now here we have the program. So y to the order, sorry, x to the power of y is very often used, and really I faced this thing when we realized a function which is called 6-hump camel plot. In Python, really, we are working with a textual presentation of the program, but for this in LabVIEW, there is a solution for it already, and also I am offering you another solution. If you right-click on the block diagram here, and you go to the mathematics palette, and then go to the elementary palette, you will find here an exponential functions. This is the function which we are interested with, x to the power of y. Here it is. So all what do you need to put this function on the block diagram? Here a terminal for x, you add the value you want. Here a terminal for y. I think it is shown as x. Yes, here it is y, here it is x, and here you get y to the power of x. Y15 and 2, here I put them specifically so that to compare the answers of both ways here, the upper code and the lower code. In the upper code here, as you see, this is a simple code where here we have an input of x. Here it is a number 15. I give it number 15. And the input of y, which is represented by this figure divided by this figure. This is y. 6 by 3 means 2. Y, I have y2. So here y, as y here is 2. 6 divided by 3 is 2. So the same y, and here number 15, and here x is also number 15. So when I run the program, I get the same answer. 15 to the power of 2 gives 225. If you go back and change the thing, for example, the x is equal to 7 and y is equal, let us be 2, so that because we know it in advance, 7 would be 49 here. So here x is equal to 7. We have to put here 7. And when we go also to the block diagram, here we need this to be 2. 6 by 3, it is already 2. Of course, you can write here 4 by 2, the same thing. 4 divided by 2, it gives you 2, which is here 2. Now, if you run the program, you will get 49 for both cases. 49, 49. So this information will be used when we shall write the expression of the objective function of the 6-hump camel function. This function, we shall investigate it and find its minimum in the coming lecture, I promise. So with this, we finish today's lecture. Thank you for listening and wishing you the best.